Hello, my name is Bob, and I'm a tutor at Raritan Valley Community College's Academic Support Center. This is our second session on statistics, and this is Module 3, which looks at normally distributed variables. The specific objectives for this module are as follows. First, we're going to look at the basic properties of the standard normal curve. Next, we're going to look at the z-score, or the standardized normally distributed variable. Next, we're going to look at finding the area to the left of a specified z-score using Table 2 in our book, Weiss on Statistics. Then, we're going to look at how we can use the TI-83 and TI-84 calculator to calculate the same Table 2 values. Then we're going to do it backwards. Once we're given the area to the left of the z-score, we're going to look at the table and find out how to find the z-score from the area to the left of the z-score. And then we're going to use the TI-83 and TI-84 calculator to do exactly the same thing. And we're going to look at a normal probability plot. So let's get started. Now, as a way of review, the standard normal curve is the bell curve. And the standard curve has a mean of 0 and a standard deviation of 1. Some specific properties of the standard normal curve are as follows. First, the total area under the curve is 1, or 100%. The standard normal curve extends infinitely in both directions. It approaches the horizontal axis in both directions, but it never actually touches it. The third property is that it's symmetric about the y-axis. And the fourth property is that almost all of the area under the standard normal curve is between -3 standard deviations and +3 standard deviations. Now let's talk for a second about the z-score. What the z-score does is it converts data from a real-world normal distribution, like an IQ distribution, which centers around 100, or shoe sizes, to a corresponding normal point on the standard normal curve. The reason we do this is that we have so much data about the standard normal curve, we can use that to project onto the actual problem we're studying. The formula for the z-score is z equals x, which is the observed value we're looking at, minus the mean, divided by the standard deviation. And again, just reviewing, x is the observed value that we have, mu, or x bar, is the mean of the observation, sigma, or s, is the standard deviation of the observations, and z is the standardized version of the normally distributed variable. Let's look at a real-world example. Suppose we had a factory, and we made ball bearings. And the ball bearings we made were about 1/4 of an inch thick. Okay? Now, the process that we have that makes those ball bearings isn't as precise. It can make every one exactly the same size. And in our factory, the mean of our ball bearings is actually 0.2499 inches, or just 1/10,000th of an inch smaller than 1/4 of an inch. And the standard deviation, the variation in those things, is about 2/10,000ths of an inch, or 0.0002. Now, we have a contract that calls for us to make ball bearings that are exactly 1/4 of an inch, plus or minus 3/10,000ths, or between 0.2497 inches and 0.2503 inches. Well, given our process that doesn't quite make those things, what percent of our ball bearings are going to be defective according to the contract? Well, this is where statistics comes in handy. We know that our ball bearings must be bigger than 0.25003 minus 3/10,000ths of an inch, or 0.2497. And so we calculate a z-score for that value. And that z-score is 0.2497, our observed value, or the value we want, minus the mean of our process, which is 0.2499, divided by the standard deviation of our process, which is 2/10,000ths, and we get a z-score of -1. And we also know our ball bearings must be smaller than 0.2503. So we calculate the z-score for that number also. Our observed value is 0.2503. We subtract the mean of our process, which is 0.2499, and divide by the standard deviation, which is 0.002. And that is a z-score of 2. So now what we're going to do is look for what is the area between -1 and 2 on our standard normal curve. The way we do that is we go to Table 2 in Weiss and look up the two z-scores. On the table on the left, we go in and we're going to look up the z-score for -1. And so we find the row that has -1 in it, and since we want -1.0, we find the column that is labeled 0.00, and we find that the z-score for -1 is 0.1587, or 15.87% of our ball bearings are going to be smaller than 0.2497 inches. Now we go in and look up the z-score for the bigger number. All right? And in this case, we know that our standard score was 2, and so we go into the right-hand part of Table 2. We find the row that has 2.0 in it, and then we look up for 2.00. In that column, we find that our probability is 97.72%, smaller than 0.2503. Now that we have the probabilities for our two z-scores, we're going to take the difference between them to find the difference. So the probability of a good ball bearing is 97.72% minus 15.87%, which is equal to 81.85%. Now we wanted to know the probability of bad ball bearings, so what we're going to do is take 100% and subtract the good ball bearings, 81.85%, and get our bad ball bearings, which are 18.15%. Well, that was a lot of work to try and figure out exactly what percentage is going to be good and bad and everything else. Is there a way that our TI-83, TI-84 calculator can help us to do that? And the answer is yes. We're going to use a function on the TI-84 calculator that's called the Normal Cdf Function. I'm going to turn my calculator on, and I'm going to clear the screen, and let's see what we can do with the Normal Cdf Function. Now there's a syntax or structure for the Normal Cdf Function. And so after the Normal Cdf Function, we need to put in our lower bound, followed by our upper bound, followed by our mean, and then our standard deviation. Let's try it for our specific problem. First thing we have to do is get to Normal Cdf. And the way we do that is hit second, and on the vars key is distributor, or DISTR, and you can see that the second function down is Normal Cdf. Let's scroll down. And we're going to hit enter, and now on our home screen you can see we have Normal Cdf. Now our lower bound was 0.2497. And we're going to separate that with a comma, and our upper bound was 0.2503. And again, we're going to separate that with a comma. The mean of our process was 0.2499, and again another comma, and then our standard deviation was 0.0002, and now a closing parentheses. We hit enter, and we get the answer 0.818594. Well, that says that 81.85% of our ball bearings are good, which is exactly the same number that we had when we calculated it using the table. So we were able to jump directly here without calculating the z-scores or anything else that we needed to do. We would then take 1 minus, and we'd bring that answer down from the prior line, hitting second answer, and hit enter, and we get 18.14% of our ball bearings are bad. And so we're able to do the calculation very quickly. Of course, we could have done it one more way, and I'm going to show you that right now. We could calculate the bad ball bearings on the left and the bad ball bearings on the right and add them together. Let's do that. Well, first we're going to hit second DISTR to get our Normal Cdf function. Okay, and now for the bad ones on the left, we got to put in minus infinity. Well, you can't put minus infinity in the calculator, there's no key for it. The closest its approximation is -1 with 99 zeros after it. And the way we do that is -1, and now we're going to use scientific notation, the letter E, and that's on the second double E key. And then we're going to put 99, and that's -1 with 99 zeros after it. That's as close to minus infinity as we can get. Put in a comma, and now our lower bound was 0.2497. 97, let's get it in there. Hit a comma. Our mean was 0.2499, another comma. And our standard deviation was 0.002, 0.0002, closing parentheses. And now we need to add to it the area on the right side, so we'll hit a plus. We'll go back up and hit second DISTR again, down to Normal Cdf, hit enter. And now our lower bound here is going to be 0.2503, we're going to put in a comma, and we need to go to positive infinity now. We put that in as 1, second, double E for the E key, 99, comma, we hit 0.2499 for our mean, comma, 0.0002 for our standard deviation, closing parentheses, and hit enter, and you can see we can jump directly to the 0.1814 that we calculated the other way. So there's how we can use our calculator to come to exactly to the percentages that we need. Now suppose we were in class and we were asked to show our work, and so we had to calculate the z-score, and we had to put the z-score into table 2. We could put the z-score directly into the calculator and get exactly the same answer that we got from table 2. Remember our z-score from the lower bound was -1? What we would do is hit second DISTR, scroll down to Normal Cdf, and hit enter. And again, now we want the area between minus infinity and -1. So we'd hit -1, second, double E, 99, comma, -1, comma, and remember our standard normal curve has a mean of 0, comma, and a standard deviation of 1, comma, and we'd hit enter, and we would get the 0.15, 86, 55, etc. that we were expecting. Now sometimes we're given exactly the opposite problem. Suppose that we were told that the area under the curve was 0.158655, etc., and we wanted to find out what the z-score was. Well, we can do that also with the calculator. And the way we do that is we hit second DISTR, and under Normal CDF, the next function down is inverse normal, which says we have the area and we want to get back to the z-score. We would hit enter, and we put in the area, in this case 0.1586, and I'm not going to put in the rest of the decimal places. We put in a comma, we put in a mean, which is 0, comma, we put in a standard deviation, which is 1, a closing parentheses, and you can see that the z-score that corresponds with that number is -1, and a little bit of variation because we didn't put in all the significant digits we had before. So if we have an area to the left of the curve, and we want to find the z-score, we use the inverse normal function, and then we put in that number, the area, the mean, and the standard deviation. Now let's move on to another example. Now suppose our manager came in and asked us about those ball bearings one more time, and he wanted to know where 90% of our ball bearings fell between. Well, we could do that using the inverse normal percentages. We would want to know what 5% were below and 5% above were. So the way we do that is hit second DISTR, scroll down to number 3, the inverse normal function. We want 5% below 0.05, comma, our mean was 0.2499, and our standard deviation was 0.0002, in a closing parentheses, and it says that for our process, the smaller, to get 90% of them, the smallest they would be is 0.24957, and then on the upper side, we'd again do second DISTR, scroll down to inverse norm, and now we want 0.95%, we hit comma, 0.2499, comma, 0.0002, closing parentheses, and on the upper side it would be 0.2502. So 90% of our ball bearings are between 0.24957 and between 0.25022 inches. So we can use the calculator to go backwards, just like we can go forwards on the normal cumulative function. Let's consider the Dow Jones Industrial Average. All of you have heard about the stock market and the way it tracks price. Suppose somebody said, what's the average percent deviation on any given day from the prior day? Well, we can go in and take a random sample of 50 days from the over 20,000 days that the stock market's been in existence, and we could calculate what was the change from the prior day. And so we've done that. And the table on your screen gives you 50 random values. The values are in the big bold print, and the date that they were selected from is in the above. And what I'm going to do is start entering them into the calculator. So we hit Stat, and we hit Edit, and you can see we have some data in there in column L1 and L2. Let's get rid of that. We're going to scroll up to L2 and clear it and scroll down. We're going to scroll over it and up to L1, clear it and scroll down. And now we're going to start entering the data. The first one is 0.945, enter. The next one is 0.782, enter. The next one is minus 0.074, enter. And now we're going to stop the tape. We'll leave it frozen here on this screen. If you want to enter the rest of the data, feel free to do so. And we'll pick it up when I'm done entering all the data. Okay, now that we've got the data entered in, let's do a histogram. And the way we do that is we hit second stat plot. We're going to turn plot 1 on. So we're on plot 1. We'll hit the enter key. We'll scroll over the on and hit enter. We're going to make sure that it's on histogram, so we'll scroll over to the histogram and hit enter. Our X data is in L1, and our frequency is we want to count 1 for every value in column 1. So we need to put a 1 in the frequency, and the way we can do that is turn the alpha lock off by hitting the alpha key and hitting the number 1. And then we can hit graph. And you can see we got something wild looking, so we're going to hit a zoom, and then zoom stat, which is number 9. Hit enter. And you can see we start to get what looks to be a reasonable histogram there. Let's see if we can adjust the window manually and make it even a little bit better. We're going to hit the window key. We're going to make our smallest value -6. We're going to make our largest value 6. Let's have our X scale, or the size of the boxes, be 0.5. We'll make our Y min be -5. We're going to make our Y max be 15. We'll make our Y scale be 1. And now let's hit a graph. And you can see there's a pretty reasonable histogram, and at first look, it looks like it's a bell curve. So let's move on and do some more analysis. The first thing we need to do is get the mean of all that data. So we'll go to our home screen. We do that by hitting second quit. And remember, our definition for mean was to add up all the values in L1 and divide it by the number of values. So we'll do that. We'll hit second list, scroll over to math, choose the fifth option, which is sum. We want to sum L1, so we hit second L1, closing parentheses, and we want that number divided by 50. Divided by 50, which is the number of entries that we had in our table. Hit enter, and we can see that the mean is 0.15708. Now we need standard deviation. Okay, well, the formula for standard deviation is the sum of all the values squared minus the sum of all the values squared divided by n minus 1. Let's see if we can calculate the values squared. We're going to go back into that table and do some editing. So we're going to hit Stat. We're going to hit Edit. We're going to scroll to column 2 and scroll up. And we want column 2 to be the sum to be column 1 squared. So we're going to put in second L1 squared and hit Enter. And now we're going to go to our home screen and calculate the standard deviation. Second quit to get to the home screen. And the first thing we needed is the sum of the values squared. So it's second list, scroll to math, fifth function for sum. The squares of the values are in column 2, so we're going to hit second L2, closing parentheses. And we're going to subtract from that the sum of the values, which are the sum of L1, so it's second list, second math, sum. We want L1, second L1, closing parentheses. We want that number squared, and we want that number divided by our number of entries, which is 50. And we hit enter, and so our numerator is 0.6894 and change. We want that number divided by n minus 1. Our n was 50, so in this case we're going to divide it by parentheses 50 minus 1, closing parentheses. So the number under the square root sign is 1.407. We want the square root of that number. We'd hit second square root, second answer to bring our calculation back, closing parentheses, and our standard deviation is 1.186. And again, we could have done all that with one simple calculation. We could have hit stat, going over to calculate, hit enter for one variable statistics, tell it we're going to work with L1, second L1, hit enter, and you can see that our mean is in fact the 15708. We have the two standard deviations, Sx, which is our sample standard deviation, and sigma x, which is our population standard deviation. In this case, we want the sample standard deviation, and it's 1.186. So we know a lot about this curve. Okay? So, does that mean that's a good normal curve? Well, one of the things that we can do is do a normal probability plot, and then we'll make a judgment about how good this curve is. So we're going to go back to stat plot, second stat plot. We're going to hit enter for plot 1, and we're going to change our type from a histogram all the way over to the normal probability plot, which is the sixth one on that list. And we hit enter, and it says that our data is in L1, and we're going to use the x-axis, so we can hit graph. And it's not quite a user-friendly window. Let's try zoom stat to make the window a little bit more user-friendly. Zoom, scroll down to 9, and there's zoom stat. And there you can see our normal curve. Well, the bulk of the data in the middle looks like it's a relatively straight line. It's pretty good, but notice those outliers. They're way off the line. Now, if we had a reason to throw out those outliers, that would be fine. We'd throw them out and we'd say, yeah, we have a normally distributed curve. But in this particular case, we do not have a reason to throw out those outliers, so we'd say the normal curve is not really a good fit. Well, why not? Let's take a quick look and see if we can figure out. Let's go back to our probability histogram. And so we can do that with second stat plot. Hit enter for plot 1. We're going to scroll down and change it back to a histogram. And we'll do that graph of the histogram, just to make sure it came back right. Graph. And there it is. Now this is a frequency histogram. And let's adjust the window from -6 to 6 with a half. And we're going to make the bottom -5 to 15 with steps of 1. And there's the graph we had before. And as I said, this is a frequency histogram. Well, if we wanted relative frequency histogram, what we need to do is to have each of these divided by 50 entries, so we could scale it down. Well, there's no convenient way to do that, but what we can do is hit Stat, and we're going to hit Edit, and we could put in column 3, 0.02, which is 1 divided by 50, and enter that column all the way down. Now, I've already put that data over in column L4, so what I'm going to do is just copy L4 into L3, and the way I'm going to do that is say L3 equals second L4, and that puts all those 0.002s in there. Scroll back, and now let's go change our frequency histogram. What we do is hit second stat plot, hit enter, and instead of the frequency being 1, we're going to make the frequency be second L3, which is where those 2's were. Hit enter, and now graph. And you can see it's pretty small. We need to adjust the window. So let's adjust the window. And the x values are okay, but now the window is going to run from the minimum value being -0.1 to the maximum value being 0.4. And now we'll do the graph. And there's the same histogram with a relative frequency. Well, why did we do that relative frequency histogram? The reason we did that is we'd like to put our normal curve over the top of it and see how it looks. And we can do that using the Normal Cdf function. So let's go to the y equals screen. We'll hit second distr, and you can see that the Normal Cdf function is the first one. We'll hit enter. And we're going to put x in for the values that we want to graph, followed by a comma, followed by our mean, which is 0.157, followed by a comma, followed by 1.186, which is our standard deviation, and a closing parentheses. And now we'll hit graph, and what we should see is over top of our relative frequency histogram is the normal curve that corresponds to it. Notice that if we hit trace, and we trace along in the bins, and we get to that bin number 3 there, which has a min of -4.5 and a max of -4. We have over 2% of our values there, much higher than what we would see on the normal curve. And if we scroll over more, when we get to that bin right next to 0, which is between 0 and -0.5, we can see that we have 26% of our data there, and yet what we have on the normal curve is much higher than that. And so when we looked at our normal probability plot, those outliers that we're seeing here are the higher values on the ends of the curve and the lower values in the middle of the curve. This tells us that a normal curve is not really a good function to look at when we want to look at the distribution of the Dow changes. So let's summarize what we saw today. The first thing we did was we did a quick review of the properties of the standard normal curve, and we looked at z-score, the standardized normally distributed variable. With a specified z-score, we used table 2 to look up the area to the left of the z-score, and then we used the TI-83 and TI-84 calculator to do the same thing without using a table lookup. We then did the opposite. We took the area to the left of the z-score, and we looked up the z-score in table 2, and we did the same thing on the TI-83-84 using the inverse normal function. We looked at percentiles for normally distributed variables, and we looked at the normal probability plot. So that pretty much summarizes what we did in this module. These podcasts are being presented by Raritan Valley Community College. Raritan Valley Community College is a 2-year college located in Branchburg, New Jersey. It serves both Hunterdon and Somerset counties as well as the other counties of New Jersey. RVCC offers a wide variety of majors, from the arts, humanities, math, science, nursing, etc. It offers both credit and non-credit courses and is a very economic option for those students either leaving high school directly or for those who are re-entering